Have you ever been on a road trip, maybe heading to a new theme park or visiting family in a city you've never seen before? You pull out your phone and type in the address, a little blue dot starts moving along a map telling you exactly where to turn. It's like magic. Or maybe you've ordered a pizza and watched a tiny car icon inch closer to your front door. How does it do that? How does this little device in your hand know its precise location on our huge, spinning planet? The answer is a system called GPS. Every day, millions rely on it. We use it to navigate our cars, find the nearest coffee shop, track our runs, make sure airplanes land safely. Before GPS, people used paper maps, compasses, and even the stars. Now satellites can guide us from thousands of kilometers up in space. It's science in action, all around you. It didn't happen overnight. Let's pull back the curtain on that little blue dot. So what does GPS actually stand for? It stands for the Global Positioning System. The name itself gives us a huge clue about what it does. Global means it works all over the world, North Pole, South Pole, everywhere in between. Positioning means it helps you find your position or your exact location. And system means it's not just one thing, but many parts working together like a team. This system is made up of about 30 satellites that are constantly orbiting our planet. Think of them as a team of super helpers flying high above our heads, always ready to assist anyone with a GPS receiver. These satellites aren't just floating around randomly. They are in very specific, very high orbits, about 20,000 kilometers. That's about 12,550 miles, above the Earth's surface. They are arranged in a special pattern, like a carefully designed net or constellation, that ensures no matter where you are on the planet, you can always see at least 4 of them at any given time. This whole amazing system was originally developed by the United States military to help soldiers, ships, and planes know their exact location anywhere in the world. But eventually, this powerful technology was made available for everyone to use, for free. A global network of machines creating a navigation grid. Imagine you're standing on a huge dark field at night and you have friends with flashlights positioned all around the edge of the field. The flashlights are waiting to turn on. Each of your friends has a special, super accurate clock and they all agree to turn on their flashlights at exactly the same time. The satellites in the GPS constellation work in a very similar way. But instead of flashlights, they use radio signals. Each of the 30 or so GPS satellites is a robotic messenger, constantly zipping around the Earth at about 14,000 kilometers per hour. That's nearly 9,000 miles per hour. That's fast enough to circle the globe twice a day. As these satellites zoom through space, they are constantly broadcasting signals down toward Earth. These aren't just simple beeps, they are packets of information. Think of them like postcards sent from space. Each postcard contains 2 very important pieces of information. First, it tells your receiver which satellite sent the message. Second, and this is the crucial part, it includes the exact time the signal was sent, according to an ultra-precise atomic clock on board the satellite. These clocks are so accurate they only lose about 1 second every 100,000 years. These radio signals travel from the satellite to your receiver at the speed of light. That's about 300,000 kilometers per second, or 186,000 miles per second. Even at that incredible speed, it still takes a fraction of a second for the signal to travel the 20,000 kilometers from the satellite down to you on the ground. Your GPS receiver, whether it's in your phone or your car, is designed to listen for these signals. It's like a catcher's mitt, waiting to grab those information-packed postcards as they arrive from space. So, you have these robotic messengers in orbit, each one shouting out its name and the time over and over again. They are powered by solar panels, keeping them running for years as they perform their vital job. Ground stations here on Earth monitor the satellites, making sure their orbits are correct and their atomic clocks are perfectly synchronized. This constant communication, from the ground to the satellites and from the satellites back down to us, is what makes the whole system work. It's a continuous, invisible conversation between Earth and space, all to help you find your way. These satellites are like the stars that ancient sailors used to navigate, but they are human-made, incredibly precise and available 24 hours a day, in any weather. They form a reliable, invisible grid that blankets our entire planet, providing the foundation for all the location-based services we depend on. It's a global utility, just like electricity or the internet, powered by science. Imagine you're standing on a huge dark field at night, and you have friends with flashlights positioned all around the edge of the field. The flashlights are waiting to turn on. Each of your friends has a special, super accurate clock, and they all agree to turn on their flashlights at exactly the same time. The satellites in the GPS constellation work in a very similar way, but instead of flashlights, they use radio signals. Each of the 30 or so GPS satellites is a robotic messenger, constantly zipping around the Earth at about 14,000 kilometers per hour. That's nearly 9,000 miles per hour. That's fast enough to circle the globe twice a day. As these satellites zoom through space, they are constantly broadcasting signals down toward Earth. These aren't just simple beeps, they are packets of information. Think of them like postcards sent from space. Each postcard contains two very important pieces of information. First, it tells your receiver which satellite sent the message. Each satellite has a unique identifier, like a name or a number. Second, and this is the crucial part, it includes the exact time the signal was sent, according to an ultra-precise atomic clock on board the satellite. These clocks are so accurate they only lose about 1 second every 100,000 years. Let's imagine a simpler example. Suppose you're in a big open park. You get a text, "I'm standing exactly 10 meters away from the big oak tree." That narrows your search, but it doesn't tell you exactly where. They could be anywhere on a circle with a 10-meter radius around that tree. Another text, "I see them. They're exactly 15 meters away from the water fountain." Now you have two clues. Two circles intersect at 2 points. You've narrowed it to 2 spots. You need one more clue. A third. "I've got them. They're 20 meters from the park bench." Draw a third circle around the bench. Where all 3 overlap, there's only 1 point. That's the exact spot. You've triangulated them. The tree, the fountain, the bench. This is almost exactly how GPS works, but in 3 dimensions instead of on a flat park map. Each satellite is like one of your friends with a clue. One satellite, you're somewhere on the surface of a giant sphere centered on that satellite. When your receiver gets a signal from a second satellite, it creates a second sphere. The intersection of 2 spheres is a circle, and that's where the 4th satellite comes in, to help you figure out which of those 2 points is your true location. So, we know that satellites are like friends shouting their distance from known landmarks. But how does your phone or car's GPS unit figure out that distance? It can't use a giant cosmic measuring tape. Instead, it does something incredibly clever with time. Remember how each satellite signal contains the exact time it was sent? Your GPS receiver, the little chip inside your phone, has its own clock. When the signal from a satellite arrives, your receiver looks at the time the signal was sent and compares it to the time the signal was received on its own clock. The difference between those 2 times is the signal's travel time. For example, signal sent at exactly 12,000 p.m. Your phone received it at 12.067 p.m., so travel time 80067 seconds. Radio signals travel at the speed of light, a constant, so distance e speed x time. The receiver multiplies 0.067 seconds by the speed of light about 300,000 kilometers per second. That gives about 2,100 kilometers to that satellite. The receiver does this at once for many satellites. Satellite A, I am 20,100 kilometers from satellite A. Satellite B, I am 21,000 kilometers from satellite B. Satellite C, I am 19,500 kilometers from satellite C. Now your receiver has the distances to 3 different satellites. You might be thinking, my phone's clock isn't nearly as accurate as an atomic clock in space. How can this possibly work? And you would be absolutely right. This is one of the most brilliant parts of the GPS design. The clocks in our phones and cars are just ordinary quartz clocks. They can be off by several seconds a day. If your receiver's clock were even a tiny bit wrong, the distance calculations would be way off. Since light travels about 30 centimeters or 1 foot in just 1 nanosecond, that's 1/1000th of a second, even a microsecond error in timing would throw your calculated position off by hundreds of meters. So, how does the system solve this problem? This is where that 4th satellite comes into play. With 3 satellites, you can find your position in 3 dimensions: latitude, longitude, altitude. Your receiver uses the signal from a 4th satellite not to find your location, but to fix its own clock. Think of it as a bonus piece of information. The receiver's computer knows that its own clock is imperfect. It performs a complex calculation, essentially asking, what time must it be for my calculated distances from these 4 different satellites to all make sense and intersect at a single point? This process is a bit like solving a puzzle with one missing piece. The receiver has 4 distance measurements, but it knows one of them, the one based on its own faulty clock, is wrong. It adjusts its own internal clock forward and backward by tiny fractions of a second until all the math lines up perfectly. Once the signals from all 4 satellites converge on a single, clean solution, the receiver knows 2 things with incredible accuracy: your precise location and the exact correct time. So your phone's GPS not only tells you where you are, but it also constantly synchronizes its clock to the atomic clocks in space. This is why a minimum of 4 satellites are needed for an accurate position fix. 3 are for finding your location in 3-dimensional space, and the 4th is for correcting the time. The more satellites your receiver can see, the better. 5 satellites, 6 satellites, or even 10 satellites, your receiver can cross-reference the data, ignore any slight errors, and produce an even more precise location. It's this incredible attention to timing, down to the billionth of a second, that makes GPS the powerful and reliable tool that we depend on every single day for pinpoint accuracy. It's a beautiful solution to a very tricky physics problem. Today, GPS is woven into the fabric of our modern world in ways that are both obvious and hidden. The most common use, of course, is navigation. It's in our cars, on our phones, in our smartwatches, giving us turn-by-turn directions and real-time traffic updates. But its reach extends far beyond just getting from point A to point B. Package delivery services use GPS to optimize routes and track shipments, ensuring your online orders arrive on time. Ride-sharing apps couldn't exist without it, connecting drivers and passengers with pinpoint precision. It's the silent partner and a huge part of our economy. The applications of GPS are incredibly diverse and often surprising. Farmers use GPS-guided tractors to plant seeds and apply fertilizer with centimeter-level accuracy. That helps increase crop yields and reduce waste. Scientists use it to track animal migration patterns. Scientists use it to monitor the slow drift of tectonic plates. Scientists use it to measure changes in sea level. Airplanes use GPS for navigation across vast oceans, and ships use it to safely enter busy harbors. Even the banking system relies on the precise timing signals from GPS satellites to synchronize transactions. It's an invisible utility that keeps our world running smoothly. So, what does the future hold for this incredible technology? Scientists and engineers are constantly working to make GPS even better. They are launching new, more powerful satellites with more robust signals that are harder to block or interfere with. This will lead to even greater accuracy. Soon, your phone might be able to tell you not just which building you're in, but which room. This increased precision could enable fully autonomous self-driving cars that can navigate complex city streets with confidence.